Hi, in this video I'm going to actually compute with you, if you throw a die 10 times, what the probability is that you have 7 sixes. That's probably quite small, but hey, what is it exactly? That's what we'd like to know. And in the course of this computation we'll discover the binomial distribution, and actually to arrive there we'll need some combinatorics. So that's altogether the content of this video. And well, let's start. Here's this problem, and you know, the sort of standard way to approach a discrete probability problem like this is to try and make a probability tree. This will turn out not to be the best idea here, but let's just start. And you have two options, namely, well, actually two options that interest you, namely whether it's a 6 or not in the first throw. So it's either 6 or it's not. And then in the second throw you ask yourself the same question. In each case, is it a 6 or not? And is it a 6 or not a 6, etc. And then again for the third throw. But as you already see, this tree is going to grow way too big. But let's put in some probabilities. So the probability for a 6 is 1 over 6, and not a 6. It's 5 outcomes that are not a 6, so it's 5 over 6. And pretty crucial here is that the probabilities are the same for each time you throw. So I can put the same probabilities here at every branch, etc. But of course we're not going to draw the whole thing, because it will end up with those branches here spreading out to 2 to the power 10, so 1024. So that doesn't work, so we need a better idea to compute this probability. But let's first look at one more step. So we can use this probability tree to understand a little bit more. So what's the probability for the topmost branch? That is, what's the probability that I throw, say, only 6s. Only 6s, so that's 10 6s in a row. That's simply 1 over 6 to the power 10. But that's not really what we're interested in. We're interested in the case that there are 7 6s and 3 times not a 6. So let's see what if we take the topmost branch, but after 7 6s we go down with only not 6s. So that start with 6s and we end with 3 times not a 6. Then what we get is 1 over 6 to the power 7 plus 5 over 6 to the power 3. All right, because we multiply the probabilities along the branches. Well, let's take one more example. What if we start with not a 6, and then we have those 7 6s. Let's write them all down for a change. And then 2 times not a 6. Actually, if you look at the probabilities along the branches, they will be the same, only in a different order. But because multiplication is commutative, we'll end up with actually the same computation, namely this one. So hey, that's interesting. As long as we have 3 times not 6 along a branch, we'll end up with the same probability. So if we want to solve our problem here, what's the probability for 7 6s? We only need to know how many branches there are with 3 times not a 6. So that is a problem from combinatorics. We have to count how many ways I can choose 3 out of 10. Where the order doesn't matter. So let's do a little bit of combinatorics, and the first thing we're going to look at is what we call permutations. Permutations. Now, what's a permutation? So if I have, for example, 5 letters, A, B, C, D, and E, I could look at a permutation from, say, of 3 out of these 5. And what would that be? That would be an ordered set of 3 out of these 5. So for example, D, A, C. Or maybe one more example. These are examples. Let's separate them well enough. So another one could be E, A, C. I say ordered, so definitely this one, where I change the order, is different. This is a different permutation than that one. So these are permutations, and now I'd like to count them. So how many permutations of 3 out of 5 are there? Well, this is denoted by 5p3, and what I do is I look at the first position. Okay, I have not chosen any of them, so there are 5 options. Then I look at the second position. There are 4 options left. And then I look at the last position, and there are 3 options left. Now, for later purposes, let's rewrite this a little bit. You can see this also as 5 times 4 times 3 times 2 times 1 divided by 2 times 1. Now, there's a notation and terminology for this multiplication of 5 times 4 times 3 times 2 plus 1, or generally the multiplication of all numbers up to a certain number, which is, well, in this case it's 5 factorial. Is 1 times 2 times 3 times 4 times 5. And generally n factorial is 1 times 2 times 3 times times n. So in particular, if you have 5 and then the permutations of length 5, this is exactly a 5 factorial, for example. So this is a pretty good terminology, and if I have 5 permutations of 3, then I can write this in short by 5 factorial over 2 factorial. And note how this 2 is 5 minus 3. So more generally, you can say permutations of k out of n, or n p k. What is it? It's n factorial, that's this 5 factorial here, divided by n minus k factorial. All right, so far so good, but it's not exactly what we need for here, because here you choose, for example, branch or throw 2, 5, and 7 as the moments where you not have a 6. But if I chosen in a different order, 5, 7, 2, it would end up with the same position. So the order doesn't matter. And when you look at permutations where the order doesn't matter, then it's not called permutation anymore, but it's called combinations. So combinations. And how do we count those? Well, as follows. If I look at a given permutation, like a permutation here of 3, then if I want to equate those, DAC with ACD with CAD, then I have to count how many of those do I have. So how many permutations of a given one. So if I have, for example, this example here of DAC, how many ways can I permute these 3 letters? That's computed in exactly the same way as we've just done. For the first position, I have 3 options. For the second position, I have only 2 options, and for the last one, so that would be 6. And generally, if I have a permutation of k out of n, then this permutation can be shuffled itself in k factorial ways. So if I want to compute the combinations, which is done like this, the combinations of k out of n, then you have the permutations, which were computed by n factorial over n minus k factorial, but each of these permutations can be permuted in k factorial ways. So if we just want the combinations, we have to divide by this number. So we divide by k factorial. Okay, so yeah, let's just for example, in this case, it would be the permutations of their space. There's just about space. So if I want to compute the number of combinations of 3 out of 5, this would be 5 factorial divided by 3 factorial and divided by 2 factorial as well. So this is 120 divided by 6 and divided by 2, and that's 10. So you see the number goes down dramatically compared to the number of permutations. All right, so there's another way actually to write this. This is n, this stresses the C from combinations, but maybe even more common is this notation n choose k. N choose k. That's the way you pronounce this. All right, so that's it, and this is what we need. So what we really want to count here is the number of combinations of 3 out of 10. And how many ways can I choose 3 numbers that are supposed to be the non-6th rows? And well, in this case, 10th rows out of 3. So there are 10 over 3 branches with 7 sixes and 3 non-sixes. And altogether, my probability that I'd really want to know from the start, so the probability for 7 sixes equals 10 choose 3 times 5 over 6 to the third times 1 over 6 times to the power 7. Did I say times? I mean to the power 3 to the power 7. All right. So there you go. What I want to do next is make this a little bit more general. By the way, I messed things up a little bit here. You could also say, okay, if I'm really interested in 7 sixes, then this should be the same as the way to choose those 7 sixes. And then usually, if we're going to generalize this in a bit, you first put the thing that you're interested in, namely the sixes, and then the stuff that you're not interested in, the non-sixes. There you go. So this end up to be the same. Actually, these two combination numbers are equal. You can think about that a little bit, why that is the case. Now, let's look at this in a little bit more formal setup. So what is this sort of experiment? It's very specific for a binomial distribution. It's actually a repetition of a very simple experiment where you have 2 outcomes. So you have a repeated experiment, repeated simple experiment, and it's binomial, and the word bi says exactly there are 2 options. So the random variable you're interested in is some sort of variable xi. There are a whole bunch of them for each repetition, which have outcomes only 0 or 1. So this is the outcome of one experiment. And it can only be 0 or 1. 0 means no success, in this case no 7, and 1 means success, which means 6 as a throw. Did I say 7? I mean 6 as a throw. So there's a very simple distribution here, because what can be the outcomes? It can only be 0 or 1. And what are the probabilities for xi to be x? I don't want the I here. It can be 0 with a chance. Well, generally for binomial distributions you would say there's a chance of P for success and 1 minus P for not success. And in our example here, of course, P, so in this case, P is 1 over 6. Okay, now you are interested in the total number of success cases, and that means you actually look at the sum of all these different xi's. So we're looking now at the random variable, which is the sum of these up to n. N is the number of repetitions, and in our example here we have n equals 10. You throw 10 times. And now what you can say in general, the probability distribution for x is given by the following formula. The chance, the probability for k times success in this repeated experiment is, well, look, you repeat it n times. In our example it was 10. So then you count the branches in which there is k times success. That's n choose k. And then the probability along all these branches will be the same. It will be p to the power k for k times success, and 1 minus p to the power n minus k for, well, n minus k times failure. And this is the general formula for the binomial distribution. Alright, so that's it. We started with a problem. We solved it using some combinatorics, and from it we generalized to this setup of repeated experiment with 2 outcomes and same chances for each one. So to arrive at this general formula for the binomial distribution, and that's the goal of this video, so we're done.